In the previous lecture, we were discussing about the 7/4 Hamming code. 7/4 Hamming code, and we had talked about the encoding process of the 7/4 Hamming code. So how do we do the encoding process? There is a generator matrix, okay, so which we call as G. Generator matrix, which is called as G, and the encoding process involves for encoding we multiply the message vectors with the generator matrix. Right, since we are doing a 7/4 Hamming code, that means this code has 4 information bits to which 3 parity bits are added to make a code word length of 7 bits, right? So the block length is 7. Out of the 7 bits, 4 bits are the information bits. So for the code rate of the 7/4 Hamming code is 4 by 7, right? So code rate equals k by n, which is 4 by 7 in this case, okay? And we did some examples of how to produce the code words. So since we have 4 information bits, with 4 information bits you have 16 possible combinations. Therefore there are 16 possible messages. So each of the message gets multiplied with the generator matrix to produce the code word. So that is the encoding process of the 7/4 Hamming code, and we did see how to produce the code word. So let me first write the generator matrix. So the generator matrix had the form 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. So the first part of the generator matrix is an identity matrix of size k. So nk code. So it's a 7/4 means it's an nk Hamming code. So out of that, k is 4 here. So we have an identity matrix here of size 4. That's a 4 by 4 identity matrix. And then we have a parity matrix, which is of the form 1. Let me write it properly. It's 1 1 1 1 0 1 1 1 0 and 0 1 1. So that's our the combined identity matrix with the parity matrix is called as the generator matrix. So to denote it as a matrix, we put the bracket. So that's our generator matrix for the 7/4 Hamming code. And to produce the code words, we multiply the message vector with the parity check matrix. We multiply the message vector with this generator matrix G to get the code word. So let me just do one particular example. So let's take, say, some code word which I did not do in the previous lecture. Let's say we have a code word, say 1101, okay? That is one of the possible 16 messages. So when you multiply this message vector with this matrix, so you multiply this row vector with the column vector, this row vector with this column vector, bit by bit, and add them together. And if the addition is an even number, if the sum is an even number, then the corresponding bit is 0. If it is an odd number, then it is 1. It's basically an XOR operation, or it's the modulo 2 addition, right? And because the first half of the matrix, or the first part of the matrix, is an identity matrix, the first 4 bits will be identical to the message bits. So we'll have it as, when you multiply this, 1 1 0 1. The first 4 bits will be identical to the message bits, and then you'll have the multiplication of this vector with these columns, with the parity matrix. So 1 into 1 is 1, plus 1 into 1 is also 1, so that's 1 plus 1 is 2. 0 into 1 is 0, so 2 plus 0 is 2. and 1 into 0 is also 0. So effectively the total sum of multiplying this with this column is 2, and 2 modulo 2 is 0. So the corresponding bit here is 0. So we get the first parity bit as 0. Then we do it for the next parity bit by multiplying the message vector with this column. So it's 1 into 1, so that's 1. 1 into 0 is 0. 0 into 1 is 0. 1 into 1 is 1. So we have two ones. So that means the sum is 2. Again, 2 modulo 2 is 0. Even number, therefore 0. And then for the last one, it's 1 into 1 is 1. 1 into 1 is 1. So 1 plus 1 is 2. 0 into 0 is 0. 1 into 1 is 1. So 2 plus 1, 3, right? So we get an odd number, and therefore the modulo 2 or the XOR value will be 1. So the parity bits for this particular message 1101 is 001. So that's how we produce the code words. Okay, I've done one more example today. I've done 3 or 4 examples in the previous lecture. Like that you can create the code words for all the 16 messages. Okay, I'm just going to show you all the 16 code words, but the calculation you can see it from the notes and work it out yourself. Okay, we've done 4 or 5 already. So in a similar way you can create the code words for all the 16 messages. Okay. Right, here we have the code words for all the 16 possible messages. Because it's a 7/4 Hamming code with 4 bits, we have 16 possible combinations, that's 16 messages. And for each of the message, we multiply it with the generator matrix and get the corresponding code word. So we've done for the first 3 or 4 in the previous lecture, and today we did it for I think 1101. So okay, today we did it for 1101 for the 14th one, and we got the code word as 1101001, which is what we calculated here, right? So we have now here the code words for all the 16 messages. Okay, that's how you create the code words. Now once we have created the code words, the next important parameter we are interested in is called as the Hamming distance. Okay, Hamming distance. So I'm going to write it here. Hamming distance. What do we mean by the Hamming distance? And we denote it by the letter D. Hamming distance, we denote it by the letter D. It is the distance between any two code words. For example, what is the Hamming distance between code word number 1 and code word number 2? Between these two, what is the Hamming distance? Between 1 and 16, what is the distance? Between 2 and 3, what is the distance? So the Hamming distance tells us the distance between any two code words, and it is defined as the number of bit positions in which the two code words are different, right? So the Hamming distance is the number of bit positions in which the code words differ. Okay, so the simplest one is, say if we look at the code word number 1 and code word number 16, in how many positions the bits are different? Code word number 1 is all zeros and code word number 16 is all ones. So every bit position is different here. The first position is 0 here, in this case it is 1, so it is different. The second position is 0, here it is 1, it's different. The third position is 0, the third position is 1. So all the 7 bit positions are different between code word number 1 and code word number 16. That means the Hamming distance between them is 7. They are different in 7 positions, right? So the Hamming distance between code word 1 and 16 is 7. So similarly, if you take the Hamming distance between, say, code word number 1 and 2, let's say we compare these two and find the Hamming distance between them. So in how many positions are they different? The first bit is the same in both, the second bit is also the same, the third bit is also the same, the fourth bit is different in the two, so that's one position which is different, the fifth bit is same, the sixth bit is different in both, so that's two positions different, and the seventh bit is also different. So totally we have a difference in 3 bit positions. Okay, so that's one bit position which is different, and that is also different, and that is also different. So the Hamming distance between code word number 1 and code word number 2, so D is equal to 3 for this case. Okay, similarly the Hamming distance between 1 and 16, so if I take the distance between code word number 1 and code word number 16, here D is equal to 7 between 1 and 16, right? Similarly, for example, if we did the Hamming distance between, say, 2 and 3, what is the distance between them? Compare it bit by bit. The first position is same, the second position is also same, the third position is different. It's 0 here, it's 1 here, so that's one difference. It's 1 here and 0 here, so that's two differences. And this is also different, so that's 3. This is same, and this is different. So totally we have 4 bit positions which are different. So therefore between code word number 2 and code word number 3 is the Hamming distance D is equal to 4, right? So that's 1, 2, 3 and 4 places which are different. So that means the Hamming distance between these two is 4. Similarly, we can compute the Hamming distance between all pairs of these code words, between 1 and 2, between 1 and 3, between 1 and 4, 1 and 5, between 1 and 6, between 1 and 7, up to 16, and then between 2 and 3, between 2 and 4, between 2 and 5, and we compute between all possible pairs of these 16 code words, and we'll find that the value ranges between 3 and 7, right? So let's do one more example. For example, if we do between, say, code word number 5 and 6, so let me do for this 5 and 6. Okay, so between 5 and 6, the first position is same, the second bit positions are same, the third also are same, the fourth, that's different, so that's one position which is different. Here it is same, here it is different, so that two positions which are different, and here also is different, so that's also one more position different. So totally they are different in 3 positions. Therefore the Hamming distance between these two, D is equal to 3. And let's do one more example, say for example between 8 and 9, okay, between these two. So in how many positions are they different? So the first position is different. Here it's 0, here it's 1, so they are different. 1 and 0, so they are different, that's 2. 1 and 0, that's 3 positions. 1 and 0, so that's 4 positions. 0 and 1, that's 5. 0 and 1, that's 6. 0 and 1, that's 7. So these two also have a Hamming distance between them to be equal to 7. So D equal to 7 in this case also. And like this you can keep computing all the Hamming distances between all pairs of code words. Okay, so out of the 16 you can take the all combinations between 1 and 2, 1 and 3 and so on, and you find all the Hamming distances between these code words, and you get different values for all the pairs. And once we have computed the Hamming distance between all the pairs of code words, the next important parameter we are interested in is the smallest Hamming distance that we get for this set of code words. For example, in this particular case, we have a Hamming distance of 7 and 3 and 4, and maybe some pairs have also 5 and so on, right? What we are interested in is what is the smallest Hamming distance that we get for this set of code words between any two code words. and that is an important parameter, and it is called as the minimum Hamming distance. So we call that as the minimum Hamming distance. Minimum Hamming distance, and we denote that as d min. Okay, the minimum Hamming distance is the smallest Hamming distance between any two code words in a given set of code words. Okay, it is the smallest Hamming distance in a set of code words. Okay, and the minimum Hamming distance has an effect, or it determines how many errors and how many errors a particular coding scheme can detect and correct. Okay, so if we know the minimum Hamming distance d min, then we can determine what is the maximum number of errors that this particular coding scheme can detect, and what is the maximum number of errors that this coding scheme can correct. So the maximum number of errors that can be detected, maximum number of errors that can be detected with guarantee. Okay, we are interested in the detection capability with guarantee. Not we are not interested in things like, okay, it can detect sometimes but sometimes it will fail. No, we are talking about guarantees here. So with guarantee is given by the minimum Hamming distance d min minus 1. So if the minimum Hamming distance is 5, that means the maximum number of errors in the code word that can be detected is 4. 5 minus 1, 4. If it is 3, then it will be 3 minus 1. 2 errors can be detected. If it's more than 2 errors, it cannot be detected, and so on. So the maximum number of errors that can be detected by this coding scheme with guarantee, that means for sure it will be able to detect it, then that is given by the minimum Hamming distance minus 1. So that is the maximum number of errors that can be detected. Okay, similarly, the maximum number of errors that can be corrected with guarantee, maximum number of errors that can be corrected with guarantee is given by d min minus 1 divided by 2, and we take the floor of it. The floor operator means, what does this symbol mean? The floor means if this answer is a fractional number, for example, if it turns out to be 2.5, then we take the answer as 2. If it is even 2.99, then we have to say it is 2. Maximum number of errors that can be corrected is 2. If it is 3.85, then it is 3. So we round it off to the lower integer. Okay, the fractional part is discarded. That is what this means. So if the answer we get here is a fractional number, we ignore the decimal the part after the decimal point, and we keep only the integer part, right? So that is what it means. Okay, so from the minimum Hamming distance, we know that how many errors that this particular coding scheme can detect with guarantee, and how many errors it can correct with guarantee, and that is the detection capability is 1 less than the minimum Hamming distance, and the correction capability is half of 1 less than the minimum Hamming distance, but the floor value of it, the lower integer, right? So with that, if you observe for the 7/4 Hamming code, if you compare all possible pairs between 1 and 2, 1 and 3, 1 and 4, 1 and 5, and so on up to 1 and 16, and then 2 and 3, 2 and 4, 2 and 5, if you compare all the Hamming distances, you will notice that the smallest Hamming distance that you get for the 7/4 Hamming code is 3. There will not be any pair of code words which are different by less than 3 bits. Okay, minimum distance between any two code words that you get for this set of 16 code words is 3. So for the 7/4 Hamming code, the minimum Hamming distance is 3. So for the 7/4 Hamming code, the minimum Hamming distance is dmin equals 3. So if the minimum Hamming distance is 3, that means what is the maximum number of errors that can be detected? It is 3 minus 1. That means maximum 2 errors out of the 7 bits in a code word. Up to 2 errors, if there are up to 2 errors in the code word, the coding scheme will be able to detect it. If there are more than 2 errors, then it will not be able to detect it. And what is the maximum number of errors that it can correct? It is dmin minus 1 by 2, which is 3 minus 1, which is 2 by 2, which is 1. So that means it can correct a maximum of 1 bit error. If it is more than 1 bit error, it cannot correct it. 2 bit errors it can detect, it cannot correct it. 1 bit error it can detect as well as correct it. More than 2 errors it cannot even detect it, right? So for the 7/4 Hamming code, the maximum number of errors that can be detected, maximum number of errors detected is equal to dmin minus 1, which is 3 minus 1 equals 2 errors. And the maximum number of errors that can be corrected is dmin minus 1 by 2, which is 3 minus 1 by 2, which is 2 by 2, which is 1. So it can detect a maximum of 2 errors and it can correct a maximum of 1 bit error, right? So that is the error detection and correction capability of the 7/4 Hamming code. Okay, why is it that it can detect only 2-bit errors? Because if there are 3-bit errors, that means one code word can become another code word which is from the same set. For example, if you look at these code words, for example, suppose we transmit the code word number 1, which is all zeros, and if this code word ends up in having 3 errors, and if that error happens in position number 4, position number 6, and position number 7, that means we transmitted this code word. What the receiver got is this code word which has 1, 2, and 3 errors, and because this code word that the receiver has got is from this set of valid code words, the receiver will think that it is a valid code word, and therefore it will accept it as a valid code word and therefore fail to detect the error. Okay, because the number of errors that can be detected is dmin minus 1, which is only 2, but in this case there are 3 errors, and when there are 3 errors, that means when the minimum Hamming distance of errors, that means one code word can get changed to another code word. In that case, the receiver will not be able to detect the errors. But anything less than that, right? If you change only 2 bits in this code word or in any code word, it will not become any other code word, because to change one code word to another code word, you have to change at least 3 bits. That's why the minimum Hamming distance for this code word or for this set of code words is 3. So since the minimum distance is 3, you need to change at least 3 positions in order to change one code word into another code word. Okay, and if that happens, then the decoder will not be able to detect the error because you transmitted one code word but it received another code word from this set of code words, so it will fail to detect it. It is from the same set. So that is why the minimum Hamming distance is an indicator as to how many errors that the coding scheme can detect and correct. Okay, so let me just illustrate that a bit more. So suppose we transmit 0 0 all zeros, the code word 0 0 0 0 0 0 0. So that's our first code word, right? And suppose there are 3 errors in this code word, and if those errors, okay, if we transmit this and if the receiver gets 0 0 0 1 0 1 1, so that is 1 error, that is 2 errors, that is 3 errors. So there are 3 position errors in this code word, but this 0 0 the received code word that we have received here is among the valid code words in this coding scheme. So therefore the receiver can't detect it because dmin is 3 and dmin minus 1 is 3 minus 1 is 2. It can detect only a maximum of 2 errors. Because we have 3 errors here, the decoder will not be able to detect it because one code word has got changed into another valid code word. So therefore the detection will fail. Okay, right, we will illustrate this with an example, and for that we'll need to first look into the process of the decoding. So what is the decoding procedure for the 7/4 Hamming code? Right, but before we go into the decoding process, I want to give you one more definition with regards to these codes, and that is called as a systematic code. Systematic code. What do we mean by a systematic code? A systematic code is one in which the message bits appear unaltered in the code word, and that could be the message bits can be will appear unaltered. It may be in the beginning part of the code word or at the end part of the code word. Okay, either at the beginning or end of the code word. Right, based on this definition, the 7/4 Hamming codes that we have seen so far, they are systematic codes. So what do we mean by that? So let's look at the table of the code words. If you look at all these code words here, the message bits for each code word, the message bits appear unaltered as they are in the code word. In this case, they are all appearing in the first part of the code word. So as it is, so 0001 we have 0001, 0010 we have 0010. So the message bits are appearing as they are in the code word. In this case, it is in the first half of the code word or the first part of the code word. It could be at the last part also. For example, if we interchanged these matrices, if we put this parity matrix and the identity matrix interchanged between them, for example, if we put the identity matrix to the right and the parity matrix to the left, then we'll have the message bits at the back end of the code words, right? So either at the front end of the code word or at the back end of the code word, the message bits will appear unaltered as they are. If that is the case, then the code words produced are called as systematic code words, and the coding technique which does so is called as a systematic code. So that means the 7/4 Hamming code that we have been discussing is a systematic code, because in all the code words the message bits appear as they are in the code word, okay, and that could be either at the front or at the back of the code word. In either case, the coding scheme is called as a systematic code word, okay. So therefore the 7/4 Hamming codes that we have been saying, we have been discussing now, they are it is a systematic code. So we have the message bits which appear unaltered in the code word, and that could be either at the front end of the code word or the rear end of the code word. Either way, we still call it as a systematic code, okay. For a systematic code, the decoding process becomes simpler. When the code words are produced in such a way that the message bits are mixed up in the code word, we call them as a non-systematic code. We are not going to study non-systematic codes in this course. We restrict ourselves to the 7/4 Hamming code, which is a systematic code. Now we can move on to the decoding process of this 7/4 Hamming code. So decoding of the 7/4 Hamming code. Okay. So far we have seen the encoding, and after encoding, by looking at the code words, we have seen some properties like the Hamming distance and the minimum Hamming distance, and from that we got to know what is the error detection capability of this code and also the error correction capability of the code. Now we will see what is the decoding process, and we will also illustrate that it can detect and correct 1-bit errors. It can detect 2-bit errors but cannot correct it, and if it's more than 2-bit errors, it cannot even detect it, right? So for the decoding process, we first create another matrix called as the parity check matrix. So in the encoding, we used a generator matrix. In the decoding, we will use what is called as a parity check matrix. So for decoding, we use a parity check matrix, which we will denote by the letter H, okay. You can get the parity check matrix from the generator matrix. So based on the generator matrix, you can get the parity check matrix, or from the parity check matrix you can get the generator matrix as well. So if you look at the generator matrix we had for the 7/4 Hamming code, generator matrix, we had it as 1 0 0 0 0 1 0 0 0 0 1 0 0 0 1 1 and 1 1 1 1 0 1 1 1 0 0 1 1. So that is the 7/4 Hamming code's generator matrix, where you had this first part, okay. So you had the first part as the identity matrix, and then you have the parity matrix, right? So to get the parity check matrix, the parity check matrix H, what we do is we take this part of the matrix as it is and write it down. So H is equal to, so we take this part of the matrix, this entire matrix, this part of the generator matrix, and write it as it is. So we write it as 1 1 1 1 0 1 1 1 0 and 0 1 1. So we've written that as it is, and because our code words are of length 7, so we are going to multiply these code words with the parity check matrix to get some result, and based on the result we can detect and correct the errors. Okay, but because this is having a length of 7, this is a row vector of length 7, that means we need to have 7 rows in the parity check matrix. So we need 3 more rows here. So the 3 more rows that we are going to put will be an identity matrix of size 3 by 3. So because we need only 3 rows, so the rows that we are going to add is going to be an identity matrix, or the rows of an identity matrix of size 3. So it's 1 0 0 0 1 0 0 0 1. So if you notice this part of the matrix, it's an identity matrix having elements 1 on the diagonal and everything is 0. So it's a 3 by 3 identity matrix. So this entire matrix is now called as the parity check matrix. So we'll put a bracket here to say this is our parity check matrix. Then what we do is, just as in the encoding process, we multiplied the message with the generator matrix, right? We multiplied message with the generator matrix in the encoding process. In the decoding, we will multiply the code word with the parity check matrix. So for decoding, multiply the code word with the parity check matrix. Okay, so what we will do is, we will take any one code word from our set of code words and then keep it without errors, and then multiply that code word with the parity check matrix and see what result we get. We'll keep the original code word as it is without any errors. Okay, and by the way, this type of decoding that we are doing for the 7/4 Hamming code, it is called as syndrome decoding. Okay, so the decoding process for the 7/4 Hamming code that we are doing now, this is called as syndrome, that's syndrome decoding. Okay, so the decoding technique is called as syndrome decoding. So we multiply the code word with the parity check matrix. So to illustrate the process, let us go and select one of the code words that we want to decode. So from this, let's choose any one of them. So let's say we choose the 12th one or the 10th one, I don't know. Okay, we'll arbitrarily choose any one of them. Let me choose this 1011 1011 010. So let me write that down. So our code word is 1011 1011 010. So that's our code word that we are going to decode. So let me just double check the values to be sure. 1011010. So we're going to multiply this code word with our parity check matrix, which is 111 101 110 and 011 and 100. That's the identity part. And 010 001. So that's our parity check matrix H. So we multiply this in the same way as we did with the encoding process, right? So we are going to multiply it bit by bit. So we multiply this entire vector with this first column vector, and we get an answer with modulo 2 addition between the bit by bit multiplication. So I'm going to do the calculations at the bottom here. Okay, so the first multiplication is, we multiply this first bit with this first bit, multiply this with the second one, multiply the third one with the third element here, the fourth element here with the fourth here, the fifth with the fifth, the sixth with the sixth, and add them all together using modulo 2 addition. that should give you some answer. So let's do that. So it's 1 into 1 is 1. So 1. 0 into 1. 0 into 1 is 0. So we add modulo 2, which is 0. The addition is modulo 2, right? And the third is 1 into 1, which is also 1. So that's 1 plus, now for the fourth position it's 1 into 0 is 0, plus for the fifth position it is 0 into 1 is 0, plus for the sixth position is 1 into 0 is also 0, plus the last one is 0 into 0 is also 0. So which is equal to 1 plus 1, that's 2. Everything else is 0. So it's an even number. So the modulo 2 addition, 2 modulo 2 will be 0 because even number, therefore the sum is 0. So the first bit that we get by multiplying is 0. Okay. Then we do the same thing with the second column. Okay, multiply the code word with the second column of the parity check matrix. So that would be 1 into 1. That's 1. So let me write it down. 1 into 1 is 1, plus 0 into 0 is 0, plus 1 into 1 is 1, plus 1 into 1 is 1, plus 0 into 0 is 0, plus 1 into 1 is 1, plus the last one is 0 into 0 is 0. So it's 1, 2, 3, 4, 5, 6, 7. We're done for all 7, right? So we multiplied this 1 into this one. So 1 into 1 is 1, 0 into 0 is 0, 1 into 1 is 1, 1 into 1 is 1, 0 into 0 is 0, 1 into 1 is 1, and 0 into 0 is 0. So when you add them, it's 1, 2, 3, 4. So the total is 4. 4 modulo 2, or XOR of 4 ones is 0, right? It's an even number. So even number modulo 2 is 0. So therefore this is also equal to 0. So we write here 0. And now we'll do it for the third column. So we'll multiply this whole vector with the third column here, bit by bit, and add them together. So let me write it down. So it's 1 into 1 is 1, plus 0 into 1 is 0, plus 1 into 0 is 0, plus 1 into 1 is 1, plus 0 into 0 is 0, plus 1 into 0 is 0, plus 0 into 1 is also 0. So we have 1 plus 1 is 2, and 2 modulo 2 is 0, right? So we get 0, 0, 0. So the output that we get when multiplying, or after multiplying the code word with the parity check matrix or the H matrix, the output that we get here, this vector of length 3 that we get here, that is called as the syndrome. Okay, so we call this vector as the syndrome, and we denote it as S. Okay, so basically for the decoding process, we are calculating the syndrome of the code word. By multiplying the code word with the parity check matrix, we get the syndrome. And when the syndrome is 0, 0, 0, okay, when the syndrome is 0, 0, 0, it indicates that the code word that we have received does not have any errors. And obviously we have taken the original code word as it is without any error. So therefore there are no errors in this. The syndrome is an all 0 vector. Therefore there are no errors in this particular code word. Okay, so when the syndrome S, when syndrome S is an all zero vector, that is S equals 0 0 0. Okay, then the code word has no errors in it. Okay, so that indicates that the code word has no errors, and obviously in our case we took the original code word as it is and we simply multiplied the original code word with the parity check matrix. Now let us introduce some error in this code word. We will deliberately flip one of the bits and introduce a 1-bit error and see what happens. Okay, so there are 7 bits in this. We can change any one of them and then see what happens to the syndrome. So we can change the bit position. Let's say we will change the bit position number 4. So 1 2 3, position number 4, it's originally a 1. We will change it and make it a 0. So I'm going to erase this 1 and make it a 0. Okay, so we know that we have changed this position. Okay, so let me mark that just for our information. So this position is wrong. Okay, we know that. Let's see if the decoder is able to find it. Okay, so when this code word gets multiplied with the parity check matrix, what is the resulting syndrome that we get? So we'll do the calculations all over again and see what syndrome we get. Let me erase this first so we can do the calculations fresh again for this set of for this particular code word. Okay, so again we're going to multiply this vector with the first column and then with the second column and then with the third column bit by bit and add them together modulo 2, right? So let me do that very quickly. So it's 1 into 1 is 1 plus 0 into 1 is 0 plus 1 into 1 is 1 plus 0 into 0 is 0 plus 0 into 1 is 0 plus 1 into 0 is 0 plus 0 into 0 is 0. So that's equal to 1 plus 1. Okay, so that's 1 plus 1, that's 2, right? So it's an even number, therefore the corresponding bit would be 0. And similarly, if we do for the second column, it's 1 into 1, it's 1 plus 0 into 0 is 0 plus for the third position is 1 into 1, that's 1 plus for the fourth position is 0 into 1 is 0 plus 0 into 0 is 0 plus 1 into 1 is 1 plus 0 into 0 is 0. So what do we get? 1 plus 1 2 plus 1 3. It's an odd number, so therefore our 3 modulo 2 will be 1, right? So the second bit is going to be, the second bit in the syndrome is 1. And similarly we'll do the calculation for the third bit. So multiplying this vector with the third column of the parity matrix or parity check matrix, so we get 1 into 1 is 1 plus 0 into 1 is 0 plus 1 into 0 is 0 plus 0 into 1 is also 0 plus 0 into 0 is also 0 plus 1 into 0 is 0 plus 0 into 1 is 0, which is equal to, so if you add all of them it's only 1. So 1 modulo 2 is 1. So we get the syndrome as 0 1 1, right? So the syndrome that we get here is 0 1 1. So the first thing we notice is this syndrome is not all zeros. Okay, so it is not 0 0 0. Therefore immediately we know that there is a problem, there is some error in this code word. So the decoder is able to detect the error, that there is some error. The next thing is it needs to find out where is the error. To find out where is the error, the decoder will compare the syndrome that we have got. Okay, the syndrome that we have here will be compared with each row of the parity check matrix and see with which row this syndrome matches. If you notice now, this syndrome matches with the fourth row of the parity check matrix. So row 4 here, 1 2 3 4, 0 1 1, and that's exactly the syndrome that we have obtained here. So that means the decoder, by comparing the syndrome with the row of the parity check matrix with which it matches, okay, it compares with all of them and sees which one matches. So because now it knows that it matches with the fourth row, that indicates that the error is in the fourth position, right? So the next job is now just to flip the fourth position from its value to the other value. If it's 0, make it 1. If it's 1, make it 0. In this case, because it is 0, it has to just change it to 1, and then we will have the correct code word. And we know, because we started off with the correct code word which had a 1 here, and we deliberately made it as a 0. So we know the error is in the fourth position, but the decoder doesn't know it. But decoder now, through its computation, has determined that there is an error, and then by comparing with the rows of the parity check matrix, it has also determined that the error is in the fourth position. To flip that bit in the fourth position to the other value, if it's 0, make it 1, or if it's 1, make it 0, and then you will get back the correct code word. Okay, so that way the 7/4 Hamming code is now able to detect the error as well as correct the error. Okay, and how does it flip the bit? So let me write it down. So if the first thing is, when the syndrome is all zeros, it means that there is no error in the code word. Okay, if the syndrome is not all zeros, okay, what does the decoder do? Compare the syndrome, compare the syndrome with the rows of the parity check matrix, parity check matrix H. So we compare it, okay, and whichever row matches, okay, the row number of H that, let me rewrite that matches with the syndrome S denotes the bit position which has an error, denotes the bit position that has error. And then the next step would be to simply flip that particular bit. How do we implement that flipping? So we need to have we call it as a mapping table. So there are 7 possible syndromes, right? Because the syndromes are going to be one of these 7 values. So we'll have 7 possible syndromes. Let me write that. So the syndromes are going to be 1 1 1, 1 0 1, 1 1 0, 0 1 1, 1 0 0, 1 0 1, and 0. Sorry, what did I do? I made a mistake here. 1 0 0 0 1 0 and 0 0 1. Okay, those are the possible syndromes that we are going to get. So these are the S values. Okay, and corresponding to those S values, we determine what is something called as the error vectors E, right? So if it is having 1 1 1, then the error vector will be of length 7, but only the first position will be a 1, everything else will be 0. 1 0 0 0 0 0. For 1 0 1, that means it is the second row of the parity check matrix, right? That means the error is in the second bit, so therefore the error vector will have a 1 in the second position, everything else will be zeros. For 1 1 0, it means the third bit is in error, so the error vector will be having a 1 in the third position, everything else is zeros. Similarly, for this is the fourth position, and for this is the fifth position, and that would be the sixth position. 0 0 0 0 0 0 1. So these are going to be the error vectors. Okay, so this table that we have, which maps the syndrome with the error vectors, it is called as the mapping table. Okay, we call this as the mapping table or a lookup table. Okay, or lookup table between the syndrome and the error vector. Lookup table. Okay, so in our case, in our example that we have done now, we got the syndrome as 0 1 1. So corresponding to 0 1 1, look at the error vector. What is the error vector? So the lookup table or the mapping table will give the decoder what error vector to use. So what the decoder will now do is, it will take the received code word and add it with the error vector corresponding to the syndrome. So the addition again here is modulo 2 or XOR operation. Okay, so from the lookup table, take the error vector E corresponding to the syndrome, S, and add the error vector to the received code word. And add, by add we mean do the XOR operation, which is the same as modulo 2 addition, right, to the code word received. Okay, so the code word that you have received is 1 0 1 0 0 1 0, right? That's what we have received here. Let's go back and see. We have received here 1 0 1 0 0 1 0, that contains an error, right? And we now know the syndrome also. So corresponding to the syndrome 0 1 1, the error vector is having a 1 in the fourth position. So we just take that 0 0 0 1 0 0 0 and add them modulo 2 or XOR, right? And when we do that, what do we get? So 1 0 is 1, 0 0 is 0, 1 0 is 1, 0 1 is 1, 0 0 is 0, 1 0 is 1, and 0 0 is 0. So now you see there was an error in the fourth position, which was here. The fourth position, which was 1, we introduced an error and made it 0, and after the decoding it has been corrected again and made it as 1. So now the decoder has been able to detect and correct the error. Okay, so the error in the fourth position is detected and corrected. Okay, and we had only a single error, right? So 1-bit error it can detect, and if you recall, for the 7/4 Hamming code, it can detect a maximum of 2 errors, it can correct a maximum of 1 error. So because we had only a single error, it is able to detect as well as correct it. Okay, in the next lecture we will do some more examples where we will introduce errors in different positions. A single bit error in instead of the 4th position, let's make it the 5th position or the 1st position, and so on. And then we will also introduce 2-bit errors and see what happens, and then we'll do 3-bit errors also and see what happens, and we'll illustrate some more details about that. Okay, right, we'll stop here for today, and we will continue again in the next lecture. Okay, thank you.